Okay, we're reading this very nice perspective by a bunch of very prominent scientists on whether there is a shift underway in the processes. Oops, I didn't mean to do that. Whether there is a shift in the processes that control the warming pattern in the tropical Pacific, which we all already know is very important, as we read some details in the first part of this podcast, of this topic. Let's continue. Maybe I'll need not just 2 but 3 podcasts for this, but it's okay. Southern Ocean cooling and aerosol forcing as another energy budget constraint on what controls the pattern. In addition to the above mechanisms which we looked at in terms of differential evaporative damping and hydrological hydrological constraints, we can also think of the interhemispheric energetics framework that constrains meridional shifts in the Hadley circulation and the tropical rain band, called the intertropical convergence zone. This is where Sarah Kang has done some very nice work. This has been applied to explain the so let's read it again. In addition to the above mechanisms based on, when I add a perspective of my own in the middle of a sentence, I often lose track, as you see. In addition to the above mechanisms based on the global budgets, the interhemispheric energetics framework that constrains meridional shifts in the Hadley circulation and the tropical rain band, called the intertropical convergence zone, or the ITCZ, has been applied to explain the remote influence of the extratropical thermal forcings to the tropical SST pattern and the PWC. That's where the Southern Ocean comes in, and Sarah has done some work on that recently. When a hemispheric contrast exists in the thermal forcing, for example, more heating in the northern hemisphere and or more cooling in the southern hemisphere, the Hadley cell shifts to induce a cross-equatorial energy flow in its upper branch, acting to reduce thermal contrast. So there is nice work by Tapio Schneider as well, showing the relation between the zonal mean ITCZ shift and the heat transports from one hemisphere into the other. It relates to this process overall. The Hadley cell shift is accompanied by a shift of the ITCZ towards the warmed hemisphere. Associated northward displacement of the cross-equatorial cross-equatorial surface winds tends to preferentially cool the central eastern tropical Pacific through the coupled dynamical processes and cloud effects, thereby strengthening the zonal SST gradient. This relationship is supported by observational evidence as well. This is a robust mechanism identified across various time scales ranging from interannual variability to centennial climate change. So you're talking about not just a tropical response, but extratropical responses inducing ITCZ response, which is manifest in the trade winds, and how trade winds affect the eastern Pacific Ocean, eastern tropical Pacific Ocean differently than the western tropical Pacific Ocean. So the additional dynamical perspectives we can read after the key paradigms. What are the key paradigms that we typically talk about when we are looking at either the energy budget constraints? We already mentioned wet get wetter, but here we're talking about warmer get wetter. And of course we mentioned Biekner's feedback without saying so, but we'll see what they mean. Warmer get wetter is a precipitation pattern change in a warming climate that is determined by both dynamical and thermodynamical processes. In the zonal mean sense, the thermodynamical process is known to dominate in the precipitation increase over regions where climatological mean precipitation is rich in the present climate, called the wet get wetter mechanism. However, the effect of circulation change, that is the dynamical response, wind response, is more important in determining the spatial pattern of precipitation change. Precipitation increases owing to moisture convergence that occurs where SST is warm relative to the surrounding area, and it's called the warmer get wetter mechanism. So slightly different, but you need convergence, right? for rainfall, rising warm air, expanding cooling, etc. Pattern effect, there is evidence that the climate feedback to surface warming is not constant. In abrupt CO2 quadrupling simulations using coupled models, the net negative feedback generally weakens in the later stages. Okay. Conversely, atmospheric model simulations driven by observed boundary conditions such as SSTs reveal that the climate feedback was more negative in recent decades. In both cases, the modulation of global feedback parameter occurs because of changes in surface warming patterns, especially in the tropical Pacific. The above time dependence of the climate feedback parameter is collectively called the pattern effect. Okay, so climate feedback effect basically overall you can think of as, for a given SST warming, what is the atmospheric and the coupled response, which determines the radiative balance and hence all the internal variability or the modulation of the internal variability by the trends. Okay. Global hydrological constraint, of course, global atmospheric column water vapor is known to increase with global mean surface warming following the Clausius-Clapeyron relationship at a rate of about 7% per degree of warming. However, the global mean precipitation increase is constrained by the atmospheric energy budget. With increasing atmospheric water vapor, the atmosphere emits more long-wave radiation, overwhelming and increasing absorption of incoming short-wave radiation. This additional net radiative cooling is compensated by increasing surface latent heat release, that is evaporation, which is equal to precipitation at some average time scale, leading to a precipitation increase estimated at 2 to 3% per decade of global mean surface warming, subject to uncertainty in the short wave absorption and cloud effect. So everything is changing. You know, short wave is coming, long wave is going, there has to be a balance. We have perturbed the balance by increasing greenhouse gases, and then warming is happening. Warming increases the thermal energy, sigma T to the fourth, but we are obviously not emitting as much as we used to because we are keeping more, which means evaporation increases, clouds increase, which affects albedo, short wave. Very complicated. Biekner's feedback is simpler. The tropical Pacific mean SST is characterized by cold SSTs in the east due to equatorial upwelling associated with a zonal thermocline slope in the ocean subsurface and easterly trade winds that are in balance with the zonal atmospheric pressure gradient. Trade winds pull up the water because divergence happens, cold water in the east, warm water in the west, SST gradient, pressure gradient, winds, and then thermocline is shallower in the east, deeper in the west. There is a balance, and if you increase the cooling, increase the SST gradient and pressure gradient, winds can get stronger. You can, start a feedback, which is the Biekner's feedback, which happens during El Niños as well, right? If trade winds weaken, the slope of the zonal thermocline relaxes, leading to the reduced upwelling and Ekman pumping that otherwise act to cool the eastern Pacific. The resulting reduced zonal SST gradient further weakens the trade winds. This is the positive Biekner's feedback that explains the ENSO growth and can also be an important process in projected future changes of the mean state. So one is acting at interannual time scales, and there is a break in the positive feedback, so ENSO damps away and dies because the trade winds pick up again, so there are waves involved and there are details. We are not completely sure whether it's just the waves or there is a recharge discharge of the warm water and so on and so forth. The wind evaporation SST feedback, consider warm SST anomaly in the northern hemisphere subtropics. The resulting low sea level pressure anomalies lead to surface southeasterly wind anomalies to the south, which weaken the climatological trade winds and thereby reduce evaporation. The reduced latent heat fluxes amplify the warm SST anomaly that started this. This is key to the mechanism of west feedback, which is further modulated by changes in boundary layer stability and low level clouds. For the future mean state change, the tropical Pacific for the future mean state change in the tropical Pacific, the west feedback has been argued to explain the enhanced pattern of equatorial warming and the southern hemisphere subtropical cooling. So, so there are these different time scales involved for radiative balance, dynamical response, evaporation and precipitation balance, and so on. So you have to always think about at what time scales you are looking at these balances. Here is a framing associated with the tropical Pacific surface warming pattern. The diagram shows the radiative forcing and climate response on the horizontal axis with different spatial scales on the vertical axis. Arrows indicate the direction of processes, and those in blue can be constrained by energy budgets, whereas those in red can be explained by the atmosphere-ocean coupled dynamics. The surface warming pattern in the tropical Pacific outlined in red is the target for understanding. Equilibrium climate sensitivity is ECS, and transient climate response is TCR. Okay, equilibrium climate sensitivity I have discussed elsewhere is basically you ramp up CO2 to twice the amount at some baseline, and then you leave it there and see how the climate responds in equilibrium. But we are continuously increasing CO2 now, so we are more interested in the transient climate response because we haven't stabilized the CO2 at any level, right? So here is the surface warming pattern coupled with the Pacific Walker cell in the tropical Pacific. So what are all the things happening? Too many boxes, too many arrows, but let's start here. Global radiative forcing, for example, greenhouse gases, they produce a delayed response in the warming pattern and the PWC, and there is a forcing response which affects the global mean energy budget and temperature, which is obviously going to affect the ECS and the TCR, and they feed back with energy constraint and pattern effect that we just talked about to the surface warming pattern coupled with PWC in the tropical Pacific, and that is interacting at a basin scale and with remote influence, let's say from the Southern Ocean and aerosols. I read only part of the Southern Ocean aerosol because there is also an aerosol story to that you should go and read. I skipped that part because I'm just cutting out many things. Remote warming and cooling, for example, tropical Atlantic and Indian Ocean and Southern Ocean can also feed back with this. There's a lot of nice work showing that the Indian Ocean warming begins to control the heat uptake in the Pacific, and hence the SST gradient. And Indian Ocean also affects the Atlantic meridional overturning, which on a slower time scale also relates to heat transports, ITCZ shift, and the hemispheric impact on the PWC that we mentioned already. And the other component, cross-equatorial energy transport, which relates to ITCZ again. So hemispheric radiative forcing, for example, aerosols and ozones that I skipped, there is an asymmetry in those, and that feedback into the cross-equatorial energy transport, ITCZ shift, winds, asymmetric East Pacific versus West Pacific response, and hence surface warming pattern coupled with PWC in the tropical Pacific. Okay, so this is shown as a one-way arrow here, but you don't know, because if this is affecting rainfall, it's likely they will also affect aerosols and ozone and so on. Okay, so looks complicated, but just keep in mind the fundamental processes. So that's the energy budget part. Moving to the dynamical perspective, atmosphere-ocean coupled processes are integral in shaping SST variability and change in the tropical Pacific and beyond. Tropical Pacific has a huge impact on global climate and weather and climate because of the massive heating in the West Pacific and all these positive feedbacks we are talking about. Here we review the dynamical mechanisms that can alter the zonal SST gradient starting from the tropical Pacific and then extending our view to connections with the extratropics and other tropical basins that we looked at here. Okay, Atlantic and Indian for sure, and there are also higher latitude connections in there. So Walker index trend, as we saw, it was a SLP gradient index, global mean surface air temperature trend, and you can see that as surface trend warming happens, the Walker trend is downward, even though you have to look at the where the observations are for the two periods 1979 to 2013 here. Model experiments are shown here, which I'll come to in a minute. Okay, so the yellow here are historical plus some future scenarios, SSP2 4.5, which is middle of the road scenario, I suspect, and abrupt CO2, abrupt quadrupling of CO2. Essentially, it's a complicated story, so the response is not linear. It has these phases in which it seems to jump. So the paper is about where we are headed. So this is the Walker index, hectopascals per decade, zonal SST gradient again in kelvins per decade. This is the global mean surface air temperature trend, and this is the zonal SST trend in the tropical Pacific, which shows a more linear response here compared to this. So this is complicated by dynamical radiative energy budget constraints. This is much more local with the Bakeness feedback and so on. So, and then observations are here, and models are not doing that very well, as you can see, and this is where you would go with observations for this period and the AMIP experiments, which are over here. What does that all tell you? That we are basically struggling with understanding the model observation differences, and yet trying to use the same models to say something about what's happening. That we'll see in the end. Okay. Role of clouds. Changes in clouds affect not only the equilibrium climate sensitivity and the transient climate response that we just mentioned, but potentially also warming patterns, of course. In the tropical Pacific, convective high clouds over the warm pool act to warm the surface owing to the greenhouse effect, whereas low clouds over the eastern subtropical reflect insolation and have a cooling effect. Associated with the tropopause rise due to greenhouse warming. You remember the tropopause, right? You have warm temperatures near the surface, cool up to the tropopause, and then warm again because of the ozone formation in the stratosphere and so on. And the tropopause is rising according to observations, and it can be explained, that also results in positive feedback or negative feedback from the tropopause movement, okay, in the vertical. So associated with the tropopause rise due to global warming, high clouds shift upward and result in positive long wave feedback, which means they allow sunlight to come in, but they trap the OLR. The process itself has been addressed with high confidence, but the net radiative effect may be small owing to cancellation with the Planck and other lapse rate feedbacks, which is complicated, so I won't go into it. You shift everything else as well, dynamics and thermodynamics. Subtropical low clouds are projected to decrease with local surface warming, and might therefore act to amplify part of the observed SST trend pattern. The local positive cloud shortwave feedback will be similarly seen if the eastern subtropical Pacific warms in the future with the uncertainty in the magnitude. So you saw that the pattern of warming in the eastern subtropical is different than the IPO pattern, as we saw in the first figure. Although there are model-based suggestions that the low cloud feedback acts to weaken the zonal SST gradient in future projections, we do not have sufficient confidence yet about the role of local cloud feedback in the recent SST pattern change. Lots of details there. Everything matters, and we know a lot of things, and yet we don't know how they add up, and models are not doing everything as observed, and sometimes you don't have observations, right? Shortwave feedbacks, all these you infer using cloud data from satellites. Clear skies, cloudy skies, high cloud, low cloud becomes very complicated, and uncertainties can grow. Okay, so next part of the dynamical constraint is ocean tunnel. Changes in the heat transport by the subtropical cells provide the mechanism often called the oceanic tunnel, which can lead to differences in tropical SSTs and their zonal gradients. Basically, you have upwelling on the equator, divergence, and then it sinks and comes back. And this happens within the subtropics, and we call that the subtropical cell in the zonal mean meridional sense. These SST changes can arise from either modulation of the rate of wind-driven overturning, with a faster overturning, strengthening the zonal SST gradient through enhanced upwelling of subsurface cool waters in the eastern Pacific, or it can weaken it in the opposite direction as well, or a change in the water properties themselves, for example, temperature anomalies transported by the climatological SSTs, which may also be density compensated and are known as spiciness anomalies. Lot of dense material there. Basically, when you have upwelling, poleward transport and back, when it comes back, it's bringing some signal, whether it's bringing a temperature anomaly because of the mean circulation, or whether mean temperature remains the same and circulation anomaly is bringing something, and whether temperature anomalies are surviving because they are compensated by salinity, so they don't get mixed away, and so on. So many details there. Basically, we don't know the correct answer. When viewed as a mechanism for transporting temperature anomalies, anthropogenically warmed extratropical water advected by the mean STC probably contributes to the projected weakening of the equatorial zonal SST contrast. So mean circulation bringing anomalous temperatures versus anomalous circulation bringing mean temperatures, and so on. Although both STC mechanisms can modulate equatorial Pacific temperature, the timing of this response can be different as changes in the wind-driven STCs occur on sub-decadal time scale, so faster time scale, whereas the advection by mean STCs occurs on decadal and longer time scales because it takes a convoluted pathway. It cannot come across the ITCZ, it has to go west and come back, and so on and so forth. Okay. Projection simulations suggest a weakening of the STCs in the northern hemisphere and a strengthening in the southern hemisphere in response to surface wind stress changes. The total equatorial subsurface convergence and surface divergence of the STCs are projected to decrease, probably contributing to the weakening of the equatorial zonal SST gradient, although the efficiency of this process remains uncertain. You can essentially think of this as the Hadley cell of the oceans, because there is rising in the tropics and sinking in the subtropics and the return flow, so similar to the Hadley cell. Tropical basin interactions, I don't know how long I am, maybe I should monitor that, and 22 minutes, so let's go a few more minutes and then we will probably need another podcast. It's okay. Tropical atmospheric teleconnections that link ocean basins have also been proposed to play a role in modulating the PWC and hence the zonal SST gradients, as we saw before. Observation in figure 2. Observational, every time I try to bring up the laser pointer, it jumps because I'm not doing it correctly. The observational analysis and modeling studies of varying complexity all suggest that relative warming in both the Indian and Atlantic basins leads to stronger equatorial Pacific trade winds and hence to an enhanced zonal SST gradient, which means the Pacific Ocean's heat uptake is being affected by the Atlantic and Indian Oceans. These interbasin relationships exist on interannual and decadal timescales and extend to include the response to human-induced warming. Recent studies suggest that the pan-tropical basin interaction is underestimated in many climate models, which is another important factor to consider when we worry about projections. Models that include a stronger and more realistic influence from the Atlantic and Indian Ocean, actually Indian Oceans, it should be Atlantic and Indian Oceans, to the Pacific tend to mitigate the future weakening of the Pacific zonal SST gradient by other mechanisms. So many feedbacks are going on that if you do this part correctly, then other mechanisms become more important in what controls the future of the Pacific zonal SST gradient. Okay, so this should be about 25 minutes. Let's stop here and do another podcast, because you have to decide how much of this how many details you want to really carry or understand. If you are not an expert, you are probably wondering what's happening. So let me just summarize here that the Pacific SST gradient has global influence. In the observations, it has strengthened, and there are many processes involved, as we saw. A naive explanation, somewhat naive explanation, was that because of the warming and cooling pattern, and because of the evaporation increase but different rate of precipitation increase, means that the vertical flux of the water vapor and evaporative water vapor has to go down, which means the Pacific Walker cell has to weaken, but it turns out that the Pacific Walker cell is actually strengthened. So we're trying to understand what the controls are in the energy budget sense and the dynamical sense, even though they are obviously not independent, right? But it's easier to understand them this way. And then we want to understand where it's going in the future, because that's going to, where the SST gradient is going in the future in the tropical Pacific, because that determines the global warming rate in many ways. So that's the crux of the matter. So we are looking at many aspects of this, and then we will conclude in the next podcast with some other details of the dynamical processes on controlling the tropical Pacific SST warming pattern, east versus west. Okay, see you in the next podcast.